Hi everyone. Today we are going to cover Neural ordinary differential equations. You can check the original paper by clicking this link. Before we move on, please make sure that you're running this IPython notebook with using GPU. In today's class, we are going to cover solvers, and we are going to implement our own Euler and Runge-Kutta solvers. And second, we are going to implement Neural ODEs by ourselves. And third, we are going to do some experiments with using the Neural ODE that we implemented. And fourth, we are going to compare the result with adaptive solvers and with adjoint backpropagation method. So first, please download this package and import these libraries. The first, solvers. A solver applies a numerical method to solve the set of ordinary differential equations that represent the model. There are two kinds of solvers. The first one is fixed step size solvers, and the second one is adaptive step size solvers. Fixed step size solvers solve the model using the same step size from the beginning to the end of the simulation. Generally, small step size increases the accuracy of the result, and at the same time, it also increases the time required to simulate the system. Adaptive step size solvers vary the step size during the simulation, and these solvers reduce the step size to increase accuracy at certain events during the simulation of the model, such as rapid state changes or zero closing events. Also, they increase the step size to avoid taking unnecessary steps when the states of the model changes slowly. So first, Euler solver. Euler solver is one of the oldest and the simplest algorithm. The core idea is approximating the solution function step by step using tangent lines. So here, we are going to make a new function that calculates Euler step. You can refer to the equation over right here. And with using this function, we are going to model this part, the difference between yt and y0. This function corresponds to f function, and t equals to t0, and dt, this means the difference between the time, and it will be t minus t0 over here. And y would be y0. Please give yourself enough time to solve this function. And please pause this video and try to make Euler solver by yourself. So I will assume that you guys have tried by yourself. And this function will return this. So this function ty corresponds to f, t0, and y0. And multiplication with dt equals to multiplication with t minus t0. So this was Euler method. And now we are going to implement Runge-Kutta method. Runge-Kutta, also known as RK, is one of the popular methods used to solve the equation. So here, as we have done earlier, we are going to make a new function that calculates Runge-Kutta method. And you can refer equation right here. So this function corresponds to f, and t corresponds to tn, and dt will be h in this situation, and h are used in these areas, and y corresponds to yn in the equation. So again, pause this video and give yourself enough time to try to make your own RK4 function. So I will assume that you guys have all tried. So K1 would be T and Y, and K2 will be t plus half dt. Yes, this is the RK4 function. And now we are going to implement your ODE with using the functions that you guys have implemented above. So this will be the Neural ODE model. For the init function, you are going to get the function, which will be the dynamic of the model. And for the forward function, we have to use the solver to solve the equation. And this y0 will be the initial value, and t will be the time step that we want our values. And solver is the kind of solver that you want to use used in your ODE. So in our situation, you'll be either Euler solver or RK4 solver. So solution will be empty tensor with the length of the same as t. And obviously, the very first time step of solution will be the y0. Within this for loop, we're going to use solvers to predict our value. So you are going to use solvers that we get from here, and within every for loop, you will get a solution. So please use this J variable, and please make yourself clear how to use within this for loop. So pause this video and give yourself enough time to how to model this Neural ODE. I will assume that you guys have all tried. So this is the right answer. So we are going to give our dynamic function to the solver, and with the time which corresponds to this t, and the difference between the time and the y value. And it will give the difference between the y1 and y0. So we will get the y1 by adding y0 with the dy. So the solution for the j step will be y1, and we will increase the j by 1, and we will replace the y0 with y1, and we go over this for loop again and again. So this is Neural ODE. And now we are going to do some experiments. And first, we are going to check our neural ODEs if we have done correctly. So in this experiment, we are going to give neural ODE, we are going to check our neural ODE's result by giving dynamic of cosine t. And obviously, the result will be sine t. So for the initial value, I will just give 0, and time step will be values between 0 and 6 pi, 6 multiplied by pi, and it will be consisted of 1500 points. So this is our dynamic function, cosine, and in forward direction, it will just give towards cosine t. So we are going to test our neural ODE, and if you remember neural ODE, it gets function in the init function. So in our situation, because the dynamic is cosine function, it will be cosine. And in forward function, we have to give y0, t, and solver. And we define y0 to be y0, which is a zero tensor, and t equals to t. And for the solver, we are going to use Euler solver. So if you visualize the result, you can see that the result came out as sine function. So we can check that our Neural ODE is correctly implemented. So for the second experiment, we are going to use toy dataset, which is spiral dataset. In this cell, we are going to generate toy dataset. The true y0, the very initial point of y, will be tensor consisted of this value. And the t is time is between 0 and 25 with 2000 data points. And A is a matrix consisted of this value. And this class lambda is the true dynamic consisted of the dataset. So in the forward function, we will do a matrix multiplication between y cubed and true A. So you can say that this true A matrix is the ground truth dynamic of this toy dataset. So with torch with no grad, we will make the ground truth dataset. So if you visualize the ground truth dataset, it will look like this. And we are going to do some experiments using this dataset. So we have to make mini batch from the dataset, and the overall process will be we will just randomly pick the starting point. So the one mini batch can start from here, and the other one can start from here. So we will randomly pick a fixed length of the spiral dataset. So one mini batch can be consisted of this area, and the other mini batch can be consisted of this area. So in the mini batch, we are going to use just 10 time step, and the mini batch data data size will be 16. And we are going to get the batches from this function getBatch. So this S is the starting point. So we randomly choose the starting points in the dataset. And this batch Y0 will be the initial value picked from the S, which is the starting point. And batch T will be just 10 lengths of time. And you are going to stack our batch Y will be consisted of 1 minute batch will be consisted of 10 Y points. And we are going to stack them. So this is how we are going to make our own mini batch. And here, we are going to make our own dynamic function. So the dynamic function, it equals to over here. So in ground truth data set, the dynamic function will be the matrix multiplication between y cubed and the true A. And for the cosine, the dynamic function is just cosine of t. And in Neural ODE, we are going to make our own dynamic function with using neural network. So the dynamic function will be defined in init function and over here. And please pause this video and feel free to make your own dynamic function with using linear layers. I will assume that you guys all have tried at once. So this is not the answer. Just for my case, I will just implement with 2 layers and tan H activation function in between. The reason why we have 2 over here is because the Y0 is consisted of 2 tensors, 2 and 0. And we're going to train our neural ODE with the ODE that we implemented by ourselves. So we will have epoch of 400 and neural ODE, and we will assign neural ODE with function that we defined over here. So we will get batch from getBatch function, and it will give us batch Y0, batch T, and batch Y. And this batch Y is the label. So we are going to predict Y with using the neural ODE that we defined. And for Y0, we will give batch Y0, which is the starting point, and T, we will give the time step. And in this case, we are going to use RK4 for the solver. And we are going to calculate the loss by calculating the mean between this predicted Y and batch Y. And for every 50 step, we are going to check our neural ODEs by just giving the true Y0. And of course, in this case, we are also going to use RK4. So if you see the result, you can check that for first 100 iterations, the ODE is not doing very well. But after it gets longer training time, you can see that the red line is getting closer to the green line. And the green line is the ground truth information, and the red line is a line predicted by the Neural ODE. So you can see that the Neural ODE performance is getting better and better as the time goes by. And for the RK4, which is fixed step size solver, it took 28 seconds to complete this experiment. And now we are going to compare the result with using adaptive solvers. And for adaptive solvers, we are going to use torch.diffq package. And this library is created by the original author of Neural ODE. And you can check the code by yourself when you Google torch.diffq. So torch.diffq library provides main interface odjoint, which contains general purpose algorithms for solving initial value problems. So to solve the initial value problem using the default solver, you have to import odjoint provided by torch.diffq, and the formulation will be like this. This function represents the dynamic function that you implemented by yourself. And y0 is the initial value, and the t is the time step. So up to this 3 arguments is exactly the same that we practiced above. And rtol and atol is the upper bound on relative error, and atol is upper bound on absolute error. So these two errors are needed when computing the adaptive step size. And this method represents the solver. So please import odjoint. And in this experiment, we are going to use the same dataset with same n iteration. So we are going to make function with the dynamic function that we defined over here. And the usage of ODE is very simple. So all you have to do is to call odjoint and put the dynamic function as function, and put the initial value y0 as y0, and put t in t, and rtol and atol as this. I just used the very basic value for this tolerance. And we are going to use Dupre5 for the solver. And Dupre5 is one of the popular adaptive step size solvers. And as similar with the above experiment, we are going to check our Neural ODE within every 50 steps. So if you see the result, at very first it doesn't do well, but as time goes by, you can see that the loss is falling and it's getting closer to the green line. So if you compare the loss, you can see adaptive step size solvers have slightly lower loss than fixed step size solver. And when you compare the process time, it takes longer than the fixed step size solver. In the second experiment, we are going to compare the result with a joint backpropagation method. So we are also going to implement a joint backpropagation using torch diffq package. The backpropagation through ODE int does go through the interval of the solver, and it's not really numerically stable for all solvers, but it should be probably fine with the default prefab method. So we are going to use ODE int adjoint provided by torch diffq, and the usage of ODE int adjoint is exactly the same with just ODE int that I explained earlier. So in this situation, as the same with above experiments, we are going to use iteration of 400 and use the dynamic function of ODE function. So in the ODE adjoint, we put function, dynamic function as function, and y0 as batch y0, and t as batch t, and relative tolerance and the absolute tolerance is the same value with the above. And for the solver, we are going to use prefab. And same as the above, we will check our Neural ODE for every 50 steps. So if you see the result, at first it doesn't do very well. But as time goes, you can see that the red line is getting closer to the green line. And if you compare the result with the above adaptive step size solvers, you can see that the loss is slightly higher. And if you compare the process time, you can see it takes almost double time. So joint backpropagation normally takes longer than backpropagation. So this is all for today's class. If you want more information about Neural ODE, please refer to this site. Yeah, thank you for listening to today's class. Thank you.